Oftentimes, recursive functions can seem daunting or complicated. However, there are sometimes easy ways to find patterns that make recursive functions worth looking for. In this particular video, we will be mainly taking a look at modular analysis of recursive functions. Let's start with a famous recursive sequence, the Fibonacci sequence. Each term of the Fibonacci sequence is defined as the sum of the previous terms. More formally, we have the following, where f of n describes the nth Fibonacci term. F is a recursive function as we have defined it in terms of itself. While the Fibonacci sequence has many different properties, what we'll be focusing on is its periodicity. That is, does it repeat? Obviously, the Fibonacci sequence does not have a period, but what about its analysis mod p, where p is an arbitrary number? It turns out that in this case, the Fibonacci sequence actually does repeat itself. We can see this with some simple logic. Notice that there are only p squared possibilities for the remainders of two consecutive Fibonacci numbers. Eventually then, a pair of consecutive Fibonacci numbers will be the same as a past pair, which means that the Fibonacci sequence is indeed periodic mod p. However, do realize that this proof only works since each new Fibonacci number is decided by the consecutive two Fibonacci numbers before it. Okay, so how do we extend this logic to other math problems? Let's take a look at a problem on the AMC 12. For each positive integer n, let s of n be the number of sequences of length n consisting solely of the letters a and b, with no more than 3 a's in a row and no more than 3 b's in a row. What is the remainder when s of 2015 is divided by 12? The first thing we look for here is a recursion formula for s of n. To do this, we will do some casework, specifically in the number of consecutive letters at the end of the sequence, where x is the value of these consecutive letters. We already know that up to a max of 3 x's can appear at the end of the sequence, so we only have 3 cases. For a sequence ending with only one consecutive letter of x at the end, there are s of n-1 possibilities. This is because the value of x is decided by the n-1th term. It must be different from that term, so it suffices just to find the number of possibilities for a sequence of length n-1, or s of n-1. Similarly, for a sequence ending with 2 consecutive letters of x at the end, there are s of n-2 possibilities. And finally, for a sequence ending with 3 consecutive letters of x at the end, there are s of n-3 possibilities. Thus, s of n is the sum of all of these cases, or s of n-1 plus s of n-2 plus s of n-3. Now, we can begin our modular analysis. However, if we analyze s of n as a sequence mod 12, the period of the sequence could be up to 12 to the third power, since each new s of n is defined by the 3 before it. Therefore, we will analyze s of n mod 3 and mod 4 instead, giving us the following sequences. The mod 3 sequence has period 13, and the mod 4 sequence has period 8. Using these patterns, we find that s of 2015 is 2 mod 3 and 0 mod 4. By the Chinese remainder theorem, we can then say that s of 2015 is 8 mod 12, and we are done. Looking back on this problem, we can see that finding recursive functions can give us a clearer view of what a function does, and thus help us to find patterns. Thanks for watching.